hope you all enjoyed the long weekend. Welcome back to 110A, and we finished grading of your midterm 2 exam. Here's the distribution. Again, the regrade request is open. I have posted a walkthrough of the midterm 2 exam. So watch it. If you have questions, you want to submit a regrade request, you have until the end of Friday to do that. Also, I posted a survey asking like how did midterm 2 go and how did our lecture go, how did our discussion go. It's basically the same survey you finished for midterm 1, right? It's the same idea. I want to know how things are going. How can we best improve for the rest? Well, we have like 5 lectures left, right? So I want to know how to best how to make our lectures work better. So next Monday, I'll give you more information regarding the final exam. So basically, the idea is the final exam will be comprehensive. So next Monday, I'll post more information, including like how many questions will be on the final exam and what's the coverage for the final exam. As you know, we are a little bit behind our schedule, just a little bit. But nevertheless, so these are the administrative updates. See if you have any questions. Nope. Okay. So back to where we left over in our lecture. So these are the last bit of lecture of chapter 5. So in chapter 5, our key goal here is to, first of all, find out what are the meanings of each terms in our thermodynamic table. We started from the standard state, like what that little knot mean. We went over what's the heat of formation. We discussed what is the conventional entropy and how are the heat of formation being measured using calorimetry experiment. How did the conventional entropy being measured and calculated, right? So those were the long derivation that we went over. So for each term, again, in this class, typically we have 2 parts. The first part is what I call derivation part. It's basically telling you what each terms are, how they were determined experimentally. And then we have the application part, meaning that how do we use this appendix table to solve for properties or quantities that we want. So in our previous lecture, we went over what is the conventional entropy. We went over how was the conventional entropy being measured. So to refresh your memory, that's this long step derivation, and we end up having the measured standard conventional entropy of SO2. And now we want to pick up to say like, okay, now we have the standard conventional entropy of each chemical species. How do we use it? How do we use these measured tabulated data to solve for properties we care about, like the entropy change of a given chemical reaction? Right, so this part, the first part sounds a little bit like a review. Remember, we have a general reaction here. You can write it as like 0 goes to stoichiometric coefficient and times your specific chemical species A, B, and C. Now, keep in mind the stoichiometric coefficient, you'll have a negative number for reactant, positive for product. And the standard entropy change of the reaction is pretty much like what we have for the standard heat of the reaction. So delta S of the reaction at certain temperature at standard state. So here this little knot tells us our pressure is at standard state, P equals to 1 bar. T means that this is a reaction at a specific temperature, right? So delta S naught. This gives us the sum of my stoichiometric coefficient times the standard conventional molar entropy of that species I at certain temperature. All right. So the application of this equation will be to use the appendix data to find out the delta S naught of the reaction. So in this case, we'll do one example problem together. It's giving us the it's asking us to find the delta S naught 298 for the reaction. or the entropy change for the reaction. So in here, first thing we want to identify my stoichiometric coefficient. So for NH4, that's -4. For oxygen, that's -3. For nitrogen, that's 2. For water, that's 6. So one thing I want to highlight is when you're looking for this number in the appendix table, you want to focus on the phase of that species. So in this case, for example, when we're searching in the appendix table, right, we want to have NH3 as a gas. So that's the one we want to use. And note that NH3 and HN3 are two different things, so don't use this one. That's wrong. I've seen people doing that. So make sure you're using the right row, find the correct information. And also you want to make sure you're looking at the correct phase, right? So for example, water liquid and water gas has different heat of formation, different conventional entropy, because one is vapor, one is liquid, right? So want to make sure when reading the question, specify the phase of your reactant and product. All right. So this question is more or less just surveying the table and try to plug in numbers. So in this case, I'll give you the number. You can check the result later on. So if you do the calculation, which is the sum of my stoichiometric coefficient times the number you find from the table, this ends up to be negative 582.53 joule per mole per Kelvin. So I want to pause here and ask you to think about, what does this delta S mean? Right, so remember we start by talking about entropy is basically telling you that's what's the probability of having a thermodynamic state. Now for gas molecules, they will have larger entropy comparing to liquid molecules. They have much more degrees of freedom, it can move around. So in this reaction, a negative entropy is telling us we have less gas molecules, right? So in this case, if we look at the reaction, we started with 7 gas molecules, we end up with 2 gas molecules and 6 liquid molecules. So this negative number actually makes sense, right? We have a decreased entropy because we have reduced our number of gas molecules in our reaction. So this is going to be a nice sanity check. It's very easy to get lost in this class, but this is going to be a very nice sanity check to see okay, we have decrease of gas, so we expect negative delta S, right? So that's a good sanity check to see, is that true for this calculation? And yes, that is true, right? So when you get an answer in this class, think about it. What does it mean? And is this number making sense? All right, so that's one quick demonstration in how to use the appendix table to calculate the conventional entropy of the reaction. The last section of chapter 5 is to take the heat of formation and the conventional entropy together to calculate the standard Gibbs free energy of the reaction. So it's similar to what we went over before, right? So the delta H of the reaction is the sum of each molar enthalpy, and that's eventually related to the enthalpy of reaction by Hess law. And then we also have the delta S of the reaction equals to the sum of stoichiometric coefficient times the molar entropy from the table. So for the standard Gibbs energy change, we can do the same to write delta G of the reaction at certain temperature equals to the sum of stoichiometric coefficient and times the molar Gibbs free energy of each species. Right. And in our table, we want to know where this comes from. Right, the delta G Gibbs free energy of formation, right? So our Gibbs free energy of formation at certain temperature for chemical species I in standard state, and along with the definition of G equals to H minus Ts. So we know that this equals to delta, the heat of formation, delta FH, at certain temperature for species I minus temperature times the entropy, conventional entropy of formation of that chemical species I. And in here, you want to also know, like, how do we calculate the standard formation and the standard conventional formation entropy of some species, right? So we'll do one example together and see what exactly does it mean, how to use the tabulated data to calculate the delta G of a species. So here's a question. Use the appendix data for heat of formation and the standard molar conventional entropy to calculate the standard Gibbs free energy of formation for magnesium oxide condensed and compare that with the listed value. All right, so what we're doing here is using the equation we just write, which is delta G equals to delta H minus T delta S, and then compare that with the tabulated data. So what does that mean? So first of all, what we're trying to, and if we also have the annotated note with the soft version, so I'm just going to do it on the board, it's easier. So in this question, first of all, we want to write out the formation reaction. So from magnesium condensed plus 1/2 oxygen in gas phase to form magnesium oxide in its condensed form. And I hope people in the back can see my handwriting. Okay. And in here, what is my standard heat of formation at 298 Kelvin of my magnesium oxide? And that's the number we can read directly from the table, right? And that equals to my negative 601.70 kilojoule per mole. Right, so that's my delta FH. What about the delta F, the standard conventional entropy of formation? So the delta F S naught of 298 of magnesium oxide. Right, so this one, remember this equals to the sum of my stoichiometric coefficient times the molar standard conventional entropy. So in here, that's the stoichiometric coefficient in the formation reaction. Right? We're asking for the delta S of the formation reaction. And in here, the S naught M, these are the tabulated data. Right? So this conventional standard entropy is never zero, not like delta H, right? So delta H of your condensed elementary step can be zero, but my delta, standard molar, my conventional molar entropy is never zero. So this then becomes a plug-in number question. So for magnesium condensed, we have negative 1 times, well, 24.80, wait. No, for magnesium, well, for the product, we have our 26.94, and then minus my reactant, magnesium condensed, that's the 32.68, and minus 1/2 times oxygen, that's 205.138. And you solve for this one, remember the unit here is joule per mole per Kelvin. We solve this to be negative 108.31 joule per mole per Kelvin. Right, again, it's a negative number. In our standard formation reaction, we have a gas, and then we end up with only one condensed form. So it's a negative entropy of the reaction. And then what we find out is the standard Gibbs free energy of reaction to be our delta H of magnesium oxide minus T delta S of magnesium oxide. Right, so this is the negative 6.1.7, temperature 298 Kelvin, and this one is the one we just solved for. Just plug in numbers using the appendix data. And this is a nice thing because once we actually plug in numbers and solve for it, and keep in mind the unit here for S and H is different. This one is kilojoule, this one is joule. So make sure you take that into consideration when doing the calculation. And you can end up have a numeric number. You can compare it with the tabulated data. All right, so this part is basically a very straightforward application of how to use the appendix data to calculate the delta G of the reaction. So that's the end of our chapter 5. Okay, so our entire chapter 5, as a quick summary, is basically we're going over this appendix table step by step. So in our class, if you divide our type of question into like conceptual and derivation, that's the first part, right? So for each of these terms, delta heat of formation, the Gibbs free energy of formation, the conventional standard entropy. So for each of these terms, we went over a careful definition. What is standard state? What is heat of formation? How are they being defined? We also went over the process in how they are experimentally measured, meaning like how the scientists get into the number in this appendix table. So these you can put it into the bracket of saying like derivation and conceptual understanding. And then we have another bracket in like how to use the appendix data to get properties we want. So that's like something we did, right? So now we're looking at a specific reaction, right? How to use this appendix data to get the calculation we want. So we have like 2 different type of problems. Now we did that for all 3 of them, like heat of formation, the Gibbs free energy of formation, and the entropy, conventional entropy of reaction. Okay, see if we have any questions on chapter 5 before we move on. All right, so now we're moving on to chapter 6. Okay, chapter 6. Now, chapter 6 is the link between something we are thermodynamically defined, which are chemical potentials, and now we're ready to use our derivations. We're ready to use the thermodynamics that you learned to link it into something we care about as chemists, right? So for example, when we have a chemical reaction and we add, say, I increase temperature, right? How will that change the reaction equilibrium, right? So when I say reaction equilibrium in a mixture of A, B, and C, it's going on some kind of reactions with each other. What's the composition of my reactant versus product? What if I add some reactant in there? What if I add some product in there? How will that change the direction of equilibrium? How will that shift the equilibrium? So in this chapter, we will go over, we'll use the ideal gas reactions as a platform to demonstrate how our chemical potentials, or in this case, linked to chemical equilibrium when we have a reaction going on. We'll focus on ideal gas reactions because it's simplified and it's mathematically easy to grab. Now, the real world is, of course, more complicated, but we'll stay with ideal gas for now. All right, so in today's lecture, we'll first talk about chemical potentials in an ideal gas mixture. So we'll spend some time reviewing chemical potential, the concept of chemical potential, and how is it linked when we talk about ideal gas mixture, like what is ideal gas mixture? How do we describe chemical potential of an ideal gas mixture? That's our first goal here. The second goal, I probably don't have time to finish, but I'll try to get started introducing what is ideal gas reaction equilibrium. How can we use our definition for an ideal gas mixture to define an equilibrium constant? And later on, we'll see how does that equilibrium constant being calculated in a specific problem by doing an example problem. And then what's the temperature dependence of the equilibrium constant? So I know I'm behind, but we'll see how far we go on our lecture, on our chapter 6. So let's get started. First of all, let's quickly review, just keep in mind, that's our definition for chemical potential. If you already forgot about it, I want to refresh your memory on the definition of chemical potential, right? So when we look at chemical potential, here's a chemical potential symbol. Alpha denotes for a specific phase. And this I tells you that's the chemical species we are caring about. Right, so here we have temperature, pressure of that phase alpha. N1, N2, N3 means these are the chemical species in my mixture. And that's being defined as a partial differential of Gibbs free energy, total Gibbs free energy of phase alpha over dN of phase alpha and species I, while everything else kept constant. We'll come back and use it very soon. So, chemical potential. So now remember, we're talking about ideal gas mixture. So let's think about chemical potential of a pure ideal gas first. Right, so a few things that we know about pure ideal gas. First of all, we know that for ideal gas, we have PVm equals to RT, or PV equals to nRT. Right, so in here, we see that my chemical potential, remember it is an intensive property. So it being an intensive property is suggesting it doesn't have a dependence on your number of mole of the system. It is being defined using how does your delta G change with respect to the number of mole of species. But the chemical potential itself is an intensive property. So in here, what we have is a chemical potential is a function of pressure and temperature. All right. What else do we know? We also know from our previous definition. Now, go back to the original definition. Thinking about a pure substance. So when we talk about a pure substance, we're talking about this I just equals to some kind of chemical. Let's just call it A, right? So instead of having N1, N2, and N, J doesn't equal to I, these disappear, these disappear, these disappear, these disappear. Right? We only have one pure substance. So that effectively becomes mu alpha as a function of T alpha, PF alpha, which is a function of the G alpha over the N alpha at constant Tp. That alpha denotes for the phase of the system. What else? We have one phase. Right, we're talking about a pure ideal gas mixture. So it's an ideal gas, it's obviously only have one phase, which is gas phase. So that means my alpha, we don't have to show it. So my mu as a function of T and P thus becomes my partial differential of G over N at constant Tp, or the molar Gibbs free energy at constant Tp. Right, so this is what we did, simplify the overall definition of chemical potential into saying for one phase, pure substance, my chemical potential is a function of Tp equals to Gm, or the molar Gibbs free energy. Right, so what else do we know about the molar Gibbs free energy? We have our Gibbs equation. right? So dg equals to negative sdt plus vdp. Or effectively, we can write d mu as a function of Tp equals to d molar Gibbs free energy, and that equals to negative molar entropy dT plus molar volume dP. All right, with me so far? So we started from the generalized definition of chemical potential, and then we worked our way to simplify that general definition in a pure one-phase ideal gas scenario. Next up, how can we further describe? Like we care about processes, right? When we talk about thermodynamics, we're always talking about a specific process in this case. Now, for an isothermal process, which is pretty easy to set up for a chemical reaction, again, you can have a water bath, right? At constant temperature, you set your reaction mixture in that constant temperature water bath. So for an isothermal process, we can further solve our d mu, or the infinitesimal change of my chemical potential, to be d mu equals to Vm dp, right? So for isothermal processes, my dt equals to 0. So this term goes to 0 for isothermal processes. And what else do we know? We also know that we have Pb equals to an RT, or Vm equals to RT over P. So we can replace this to be RT over P for an isothermal processes of an ideal gas, a pure ideal gas. Right. Now, instead of writing the du, we want to talk about the initial state and final state. Right? Imagine we have a isothermal processes starting from P initial to P final, or the change, the delta of my chemical potential. And that gives me the integral here from P initial to P final. We solve that integral, we get RT ln P final over P initial for ideal gas. Right, so these should be very quick review on what you already know. Now, introducing our initial state as standard state, or replacing my P initial as my P naught equals to 1 bar. Then we can write out a general expression of mu T P equals to mu naught, which is a function of temperature. That's a standard chemical potential at 1 bar, plus RT ln P over P naught. Right, so in here, we're just replacing this P final with any pressure, P initial with your standard 1 bar pressure. All right. And now before we move on to talk about ideal gas mixture, let's spend one more minute looking at what does it mean if we plot this equation out. So here's the plot of this equation. On the y-axis, that's the mu minus mu naught. So if I move this one to the left, that's the mu minus mu naught. On the right-hand on the x-axis, that's P over P naught. So this plot is a logarithm function. My R is always positive, it's a constant. My T is always a positive number. So this is the typical logarithm function. Now let's just look at some points on this graph and try to think about what does it mean? What's the physical meaning behind some point on this plot? Let's say, imagine I'm putting at this point here. What exactly is happening at that point? So at this point, we can see that my P over P naught is approaching 0. Or the other way to put it, my standard pressure is, well, it's just 1 bar. So this ratio approaching 0 is telling me my pressure is approaching 0 of the system. Right. And in here, my pressure approaches 0. It gives us my chemical potential is approaching negative infinity. And does it make sense to us from a physical perspective? Right, so what else do we know about the system? So when you think about an ideal gas, let's say in a chamber, where the pressure is very small, then its chemical potential is approaching negative infinity. The chemical potential is also very small. So remember, what's the physical meaning of chemical potential? The relative, like large or small, of the chemical potential gives you a way to predict what's the direction of your chemical species flow. Right? Remember the comparison we made, like temperature. The heat always transfers from your higher temperature object to the lower temperature object. Temperature is the intensive property telling you the direction of heat flow. Chemical potential is the property, intensive property, telling you the direction of material flow. Right? So does it make sense? Of course it makes sense, right? You have two chambers, one with higher pressure, the other with lower pressure, both containing ideal gas. Now I put these two chambers in contact with each other. Obviously, the material is going to flow from the higher pressure one to the lower pressure one. And the reason behind it is we have the chemical potential to be different. Right, so I'm trying to make a connection here with what you already know into, again, like what exactly is behind some of the intuitive observation in our life related to thermodynamic properties. All right, so this part should be a quick review in what we already know. And now we're ready to talk about ideal gas mixtures. So what are we having here? We want to first give ideal gas mixture a definition. And then we want to use something we defined before, which is the chemical potential of a pure ideal gas substance, into describing ideal gas mixture. Right, so in this part, let's look at the definition. First of all, we have PV equals nRT. So that's our ideal gas law. We want it to still hold true for our ideal gas mixtures. But in this case, instead of having only the PV equals nRT, we now have N total, right? So if you think about a process involving like A ideal gas plus B ideal gas goes to C ideal gas. Right, so in here, my N total, well, equals to NA plus NB plus NC. Right, so for each chemical species, we have PV equals to nRT. So my total pressure equals to N total times RT. All right, so that's the first criteria. The second criteria, I want to spend a little bit more time here looking at it. So thinking about a equilibrium condition. On the left-hand side, well, thinking about a chamber, on the top, we have ideal gas mixtures, like my A, B, and C, at some temperature T and P. And for each species, its partial pressure equals to its mole fraction times the total pressure. All right, so do it one, think about it. So let's say my total number of mole gives me my mole fraction of each species. Let's say they're evenly distributed, right? Each have 1/3. So my partial pressure of my species A would equals to the mole fraction of A times my total pressure P. all right? And thinking about the process, how does this setup simplify? Like what we have? What do we have from the previous definition is we know what is the chemical potential as a function of T and P of a pure species. So this star means that's the chemical potential of a pure substance equals to mu naught of a pure substance as a function of T plus RT ln P over P naught. Right, so the star means that's a pure substance. This is something we just derived for a pure substance. So in here, if we think about this equilibrium scenario that we can construct for ideal gas mixture, we want to say that on the top, we have our ideal gas mixture at temperature T and P. Or in the other way, on the top, we have mu I, which is the chemical potential of my substance I in the mixture as a function of temperature, pressure, its mole fraction, chi I, and also something else, right? And also all the other mole fractions. So that's the top part. With me so far? What about the bottom part? So on the bottom part, we said that the bottom part will be at the partial pressure of the species I. But on the bottom part, we only have that pure gas involved. So for an ideal gas on the bottom part, we have mu I of this pure species as a function of temperature and Pi star. And this Pi star equals to Pi. All right, so if we put it in this A, B, and C example, is that we have one chamber containing A, B, and C. And for this one, if we're focusing on A, we can write that mu A as a function of T, P, chi A, chi B, chi C. Right, so that's in my top chamber over there. Now we set it up in contact with a bottom chamber containing only A. Now in here, in order for these two chambers to be in equilibrium with each other, we separate it by a thermally conducting rigid membrane that allows only A to permeate through. So B and C will not permeate through. But in order for my A to remain equilibrium with each other, the right-hand side, my pressure must equal to the partial pressure of A on the left-hand side. Right, so the pressure of my species A must remain same on both sides of the membrane so that we have equilibrium. All right. So what is the chemical potential here? So the chemical potential on this chamber, we must have mu A. Right, now we can put the star on there because in this chamber, it only have our pure gas A. Right, so this mu A as star is only a function of temperature, which is kept constant, and partial pressure of A as a pure species. All right, and this PA star equals to my partial pressure of A in that chamber. And that equals to my my total pressure times the mole fraction of A. And since these two are in equilibrium with each other, this term here, mu A, must equal to this term here. Right, so these two chambers are in material equilibrium with each other. They must have the same chemical potential. With me so far? Or if I just put it onto what we know, what we're writing is using that chamber to write out this expression. Right, so this is the one we're writing down, and that equals to the chemical potential of the pure substance A with a star, tells you that's pure, as a function of temperature and the partial pressure. Or I can further simplify it into mu I star T Pi for ideal gas mixture. All right. And now since we're looking at my chemical potential of a pure substance, we can use this equation to describe species in my ideal gas mixture. Right, so this one is true for pure substances. And then we build up a chamber to demonstrate like the chemical potential of my species A in that mixture is the same chemical potential as that species A as a pure substance with the same partial pressure. Right, so we can use this equation, and that's what we call the fundamental thermodynamic equation of an ideal gas mixture. All right, so the logic here is we started from a pure substance, pure ideal gas, and derived this equation. That's a review. And then we build up a system where you have chambers of ideal gas mixture and the pure substance in equilibrium with each other. Because they're in equilibrium with each other, we can derive to say, hey, these two chemical potential must be equal to each other. All right, and then we translated this equation for pure substance into describing ideal gas mixture. All right, and that's where this equation comes from. All right. And now what we can do, now we have this fundamental thermodynamic equation for ideal gas mixture. Obviously, we can solve for these kind of problems by plugging numbers to solve for delta G. So in this one, I'm just going to quickly set up the problem for you. We know that mu equals to Gm for pure substance. Right, so in this case, we're asking for delta G. That equals to G final minus G initial. Right, so in here, we have an expression for my chemical potential. We have our P final, we have our P initial, and we have our number of mole. So just plug in the numbers and solve for the answer. All right. So this question, I'm not going to plug in the number with you, but I'll give you the answer and ask you to think about what's the physical meaning behind that number. So in this case, we'll solve this delta G, and the number we get is negative 2305.1 joule. So what does that mean? Right, so in this case, we solved for delta G. And we know that delta G equals to delta H minus T delta S for this isothermal process. And since we're dealing with ideal gases, so delta H is 0 for ideal gas isothermal processes. And what does that mean? So a negative delta G tells me that my delta S must be a positive value. And intuitively, does that make sense? Right, we're reducing the pressure of the system. Naturally, we're increasing the volume of my system, right? So my entropy will go up, right? So intuitively, it also makes sense. So I know that this class we have so many equations, but once we have a number, looking at whether it's positive or negative always can give you an intuitive result. Like, does this make sense to me from the physical perspective of the question? We're reducing the pressure, we're increasing the volume that my gases occupy, so my entropy should go up, and it is a positive number. All right. So this is the part we used, or we defined the ideal gas mixture. We built a link between ideal gas mixture to the chemical potential of a pure substances with the partial pressure defined. And now we're ready. Once we have a mixture of my A, B, and C, right, we're ready to describe the chemical reaction between my ideal gas mixtures. Right, so the first step is to put my reaction and product together all in the same chamber. And the second step is, well, now they start to react with each other. How do we describe the chemical reaction? So I'll get us a little bit started and we'll pick up where we left over. So before we define the equilibrium constant, I want to quickly refresh your memory into what we know about reaction equilibrium. So in a typical reaction, right, again, you have zero in equilibrium. You have the sum of your stoichiometric coefficient times your species. Now in here, what do we know about reaction equilibrium? First thing, we know that for any kind of material equilibrium, we have my chemical potential, mu I, the Ni sum to be zero at material equilibrium. All right. What else do we know? So in our previous discussion on reaction equilibrium, we also went over to say like the change of number of mole of each species equals to the stoichiometric coefficient times the infinitesimal change of the extent of the reaction. Right? Remember, we went over the discussion. Once you write a balanced equation, you can and give you what's your initial state, what's your final state. You can calculate what's the extent of your reaction. Right. So a positive number means a forward reaction. Negative number means a backward reaction. So plugging this number in here into my DNI, our original condition of material equilibrium becomes mu I times stoichiometric coefficient times dc, the extent of reaction, equals to 0. And remember, this is at material equilibrium. Right. And what else do we know? We know that this one, the infinitesimal change of your reaction extent, this can never be 0, right? Even at equilibrium, you still have like infinitesimal movement of your reactant and product. So effectively, what we derived before when we talk about reaction equilibrium is that this term, my mu I times my stoichiometric coefficient, must add up to be 0. All right. So what does that mean if we look at a general reaction? So in here, what do we know? We have a general reaction. We have your stoichiometric coefficient. For my chemical potential for ideal gas reactions, we have our expression here. That's basically this one. A little bit different. And we have this expression to write out for our chemical potential. Right, so taking these together, we have a way to write out a function which tells me like these summed up must equal to 0. So in our next lecture, we'll use this relationship to come up with a definition of equilibrium constant, and then talk about the relationship between equilibrium constant and delta G of the reaction. We'll do one example together and also look at the dependence of the equilibrium constant on reaction temperature. So I know I'm one more lecture behind, but we'll see how much I can go. I'll see you next Friday. And that's all the time I have.